to equation 4.1. As we now understand equation 4.1, the average L and the average D must be weight averages. But this is only true if the length and the width of the particles are not correlated. In figure 4.2 on page 106, you are plotting the length distribution and the width distribution in separate curves, not in one three-dimensional graph. This three-dimensional graph would have given you information about those correlations. Have you looked at any correlations between the length and the width of your tubes?
I will later open it. Thank you for the question. I didn't do the correlation of the length and the diameter, but to go back to the equation 4.1, where I have shown the equation itself is valid only if the aspect ratio goes far above 1. So if I'm going for because in my case the aspect ratio is also starts from a 20 or 25, something like that. If suppose my particles are going to be having the aspect ratio like 1 or 2 or 3, then they are correlated, then this result will not fall like this. In my case,
I don't think I agree with that at all. I think if you follow the homework that my colleague has given you, then you would get an expression 4.1 which is different, which is given by the same constant C times the average of the length times the diameter squared over the average of the length squared times the diameter.
mm-hmm.
So that means that if there are correlations, that will impact upon this volume fraction.
But I believe then there is no correlation.
Yeah, but have you measured this? I mean, believing is one thing. You have to.
No, I didn't. To be honest, I didn't measure that. But
so then we have another bit of homework then to do.
But
I'll be asking you tomorrow, okay?
Okay.
Okay, let me just leave it at that. If I have a little bit of time left, I would like to take you also to section 3, where you look at spin-coated polymer latex CN2 composites. Spin coating aligns carbon nanotubes, and this is of course extremely important to the conductivity of, well, the anisotropy of the conductivity of the thin film. Now, the way that you quantify the alignment of the nanotubes is with, as far as I understand it, relative to a spin coating direction, rather than actually measuring the preferred direction and the degree of order relative to that preferred direction, so that you can quantify the angle between the preferred direction on average and the spin coating direction. So people in liquid crystals, they make use of the tensor in tensor analysis of the orientation of the particles. So have you done that? Or?
Actually, the examples what I've shown in section 3.6, it is just to show that example how they can measure the orientation of the rods. So, of course, we can do the systematic study on measuring at a different, by placing the grids itself in the different places of the spin coater and measuring how the orientation is changing relative to the spin coating direction, and also measuring the conductivity. But I didn't do that. In this example, is just to show that you can measure the orientation of it.
But I think it would be useful, because you are saying in your thesis that you've got a global orientation, but locally you've got deviations from that order. What you can do is measure or calculate from your images correlation functions of the degree of order. And not only that, also the spatial distribution of the main body axis vector that the particles seem to align along, which might be different from the spin coating direction.
Yeah, true. But here, this specific example is just to identify what is representative. That's why you can see in page number 78, if I do the same orientation analysis, I can see completely two different code in page number 79. So, I mean, the analysis, what I did is just to show how much what are the variations are there, and
but why not calculate in the metabotic plants then? I don't understand why.
yes, it is possible, but if I make a separate paper out of it or a separate systematic study out of it, yes, I do it.
Okay. Do I have more time?
Yes, sure, please.
Then I would like to. Right, let's go to chapter 5. So that will be page 139, where you look at the electrical conductivity of multi-wall carbonate fused polymer composites. So figure A gives you the conductivity as a function of the C&T volume fraction, and figure B gives you, well, the critical scaling that you expect close to the percolation threshold. Now, I would like to ask you, how on earth are you able to extract from figure A the percolation threshold for most of the curves?
Why not? I mean, I believe
Well,
you have to go.
I'm not seeing a flat bit or a curvy bit and then a different curvy bit.
Yeah. I mean, I exactly forgot which regime I chose for the figure A. I mean, you're talking about the blue curve, right? The solvent test curve.
I can't really make out the colors very well.
I mean, you have to. I chose the region which is insulating, and I chose the region which is already conducting, and then finding the region somewhere in between which one fits properly, and that gives the.
Yes, but the choice of your percolation threshold hugely influences the scaling exponent that you get. And I was, surprised that you have 4 digits in your scaling exponent, which I'm afraid I don't believe.
I'm not sure how.
Because it depends on your percolation threshold. So this is known.
Why not? That is. I believe that is also influenced by the exponent, the 2.4, 2.1, 2.8, which I have shown, and I believe that is also influenced by the exponent. So you may get the higher core R square value, but it also shifts the exponent because.
Yes, that's exactly what I'm saying.
Yeah. So I'm getting a
So
different exponent.
I'm not sure I believe those exponents, but certainly not to 4 digits. Anyway, thank you very much indeed.
Okay.
I'm done.
Thank you. This will answer your questions. Then it's now the secretary of the committee, Professor Tuinier, who will continue with the proposition.
Thank you. Geachte promovendus, congratulations with the appearance of your thesis on nanoscopy. I was aware that nano is getting more and more fashionable, leading to journals like Nano Letters, cars that are called Tata Nano. And I even recently saw a restaurant which was called Nano's Pizza. But thanks to your thesis, I now also know that nanoscopy exists. I think your thesis contains very interesting and relevant work and addresses a wide range of aspects of the analysis of conductive composites. My first question is on chapter 1, the introduction, on page 19. Maybe just a question out of curiosity. You mention various scattering and microscopy techniques in order to investigate the morphology of materials. In the beginning of section 1.2 on page 19. And you mention various techniques, but you also you do not mention, for instance, neutron scattering or photon microscopy. These kind of techniques you don't mention at all. So my question is, out of curiosity, why did you select did you make such a narrow selection?
How will I upon it? Thank you very much for the questions. Why I chose only very few characterizations, only these characterizations you can find in this thesis. Yes. So that is the main reason. Of course, you can do neutron scattering, Raman spectroscopy, and other scattering also, light scattering, DLS, but it all comes in the scattering, what I want to mention here, that you need a model to identify what you are seeing, to see what you should have a pre-knowledge before you're going to the analysis what you're going to see. But in case of microscopy, you don't know that. You can just go and see whatever, and then you understand, okay, this is what it is. So, of course, I can write all the categorization, but I believe basically this scattering itself is a model-based technique, which all falls within the same category of non-intuitive categorization.
Thank you for that answer. I would now like to move to chapter 2, where you report an optimization of image contrast for beam sensitive materials. And you perform interesting analysis on the influence of the, for instance, of the camera length. If we look at page 41, you define the camera length in figure 2.1a. And you made experiments, and you also made Monte Carlo simulations. And this agreement is quite good, yeah? It's sometimes even excellent. As, for instance, is shown on page 47, where you compare the simulation and experiment. Also in your introduction, you mentioned this. But in the appendix, you on page 59, you have carefully studied the difference between simulation and experiment as a function of the camera length, upon varying also the section thickness. And you vary the section thickness between 100 nanometer and 1 micron. And these simulations seem to be shifted to the left, so to larger camera length compared to experiments for small thickness, and to smaller camera length for thicker sections. And why do you think there is this shift?
The problem with experiment is you don't know the exact thickness. You do microtoning, you believe that it is 100 nanometer, but actually it would be 150 nanometer or even sometimes 200 nanometer. So, but in simulation, you fix the thickness exactly 100, 200, whatever you want. So I believe this is mainly due to the section thickness variation in the experiment, which shifts the curve a little bit. So if you see page 47, where the simulation and experiment at certain specific camera length, it shifts. So in case of 1 micron thick section, the section thickness itself, I don't think it is 1 micron. It would be something like 800 nanometer or 900 nanometer. But in case of 100 nanometer thick section, it would be 150 nanometer or something. So this is the same effect what you are seeing in page number 59 also, that because of the fluctuation in the section thickness, there is a little bit shift here and there.
But for me, it seems a bit slightly systematic, so I was wondering whether there is some explanation for this.
Yes, I mean, sorry to interrupt you. The model which I'm using here is also, it plays an important role, because there are several models. I used one specific model particularly for multi-scattering, and this model does not use the usual Gaussian approximation which other models use only for the short angles. The models I use, because I'm going and analyzing for the thick sections also, there are so many electrons which get scattered to the higher angle range. So I want to consider those electrons also. So I used a different model where even the tail of the Gaussian is considered in the calculation. So that model may give a different answer when you are checking with the 100 nanometer thick section, because at high angles it won't get scattered to high angles. The 100 nanometer thick section, the scattering will be less in the high angle. So I believe the model also plays an important role. So depending on the section thickness, we have to change the model also. That could be another explanation, reason for this shift.
And I estimated that when you, if you vary this thickness, that you make a bigger error when you make small slices, and smaller errors when you have
sense there's error in the section thickness
Yes,
while preparing the section, while defining the section?
exactly.
Yes, it would influence, but I didn't consider. Yes, of course, it would influence, but yeah. Even if it influences, I don't think that is going to make a huge difference, because the scattering of 100 is going to be almost similar to scattering of 150. But the scattering of 150 would be different for 8 compared with the 800 nanometer. So that even the difference when you are 800 and 1000 nanometer section thickness, so even there is a 200 nanometer section thickness difference, the error would be same as the previous one, 50 nanometer section thickness of 100 nanometer and 150 nanometer. So I'm not sure, but I would argue like this: there won't be much difference in the error bar.
Okay. I would now like to go to chapter 4. Which seems to be of interest for many members of this committee. Where you, well, for instance, you describe the random backing of the long rods with the random contact model. But in this random contact model, you assume that the contacts of the rods are uncorrelated. Can one still presume these uncorrelated contacts also for flexible rods?
I don't know, but my rods are not flexible. So my rods are stiff, so I don't think they can bend or do anything. So I'm not really an expert in this system, but in my case they are not flexible, so I don't think it influences.
On the bottom of page 107, you write, in order to quantitatively analyze the randomly packed carbon nanotubes, the results were fitted to a widely accepted RCM. But what are here exactly the free parameters?
What do you mean, which three parameters?
Well, do you also fit here this alpha as a free parameter?
Yes, I use the alpha because of the real length of the carbon length and the aspect ratio of the carbon nanotubes. Because I'm doing this end-to-end distance, I'm not really measuring the complete length of the carbon nanotubes. I'm assuming I'm approximating the distance by the end-to-end distance. So there, just to show is there any difference on the real length. So that is what I correlate with the alpha, with the exponent. And yes, I can see that alpha is increasing slightly. If I think in page number. In page number in appendix. Page number 121. Sorry, 122. I can see that alpha is going to 1.06. So just to make correction for the aspect ratio, what I'm approximating, I included that alpha factor, but I believe that is not making a huge difference in the overall analysis itself. So which can be neglected. It's just details which is not making a huge difference here.
Okay.
you, Professor Tuinier. Then it's my pleasure to give the last 10 minutes to the co-promoter, Dr. Kulik.
I also would like to join my colleagues in congratulating you on the completion of the fine thesis. My questions will, of course, go more into the imaging part. And for that, I would like to challenge your statement that now you have developed STEM towards a characterization tool. For instance, in one of the standard textbooks in electron microscopy, Williams and Carter, there is a statement that since the invention of the electron microscope, only about a cubic millimeter has been studied by high resolution TM. I mean, as a backup of the envelope calculation. Now, the tools that you develop, how quick can you do that? And is that now overcome?
Zeker the co-promoter. Thank you for the question. I think that is the best part of my thesis, that we are not limited by, by the usual 100 years back how the electron microscopy people are using to analyze the material. In my case, the largest image what I acquired was 0.1 millimeter. So I would say yes, it is keep on changing. So even if you are going for the further thick section, even if you are automating the process even further, so I believe that we can just leave these old books.
So then, would you be able to make an estimate of how much time it would take with the tools that you develop to acquire this 1 cubic millimeter nowadays?
Yeah, for me it takes 3 days, three and a half complete full days, including the image processing and the stitching and all these things. It will take maximum 5 days. So yeah, so I think we are doing a good job.
So actually, it will be becoming much cheaper in time.
Yes, it becomes much cheaper and we get more information. Yes, I believe that these techniques are developing, and I think we are on the right track, and we can close the old textbooks.
Thank you very much. Now I'd like to take you to page 183, where you're doing the template matching or cross-correlation of templates into your three-dimensional carbon nanotube network reconstruction. Now, the same technique actually was invented in biological sciences. Is applied to study the distribution of macromolecules in cells, and is there rather successful. And it is called now as approach visual proteomics. So, why do you think is it so difficult to implement it, a similar approach or the same approach to synthetic materials?
First of all, the problem with the synthetic materials, at least in my case, is the polydispersity. The carbon nanotubes which I'm using, they are polydispersed, and I believe that most of the synthetic materials, whatever you're going and getting, they are polydispersed. Very few materials in the real world that exist in mono, of course they exist in monodispersed, but in our case we are more interested in polydispersed. So when you're going for the polydispersed material, the templates, whatever we are matching, is also needs to be tuned to incorporate all the length scales. So in biology, the most of the problems which I have noticed is they create one template and they use it for the entire analysis. But that is not the same case for me. I have a difference in length, I have a difference in diameter, I have a difference in inner diameter, outer diameter. So it is more complicated. And one more thing is the contrast. In biology also the contrast plays an important role, but here in my case, because of the noise and everything and the difference in the templates, it makes the problem much complicated than the biological system. So I believe it is more to do with the system itself, what we are analyzing.
So to paraphrase you, a synthetic system is more complicated than itself.
Yeah, true, but at the same time I say that the system which I chose to do is a difficult one. Because that is the problem, because everybody already done the one template things, one template matching. But okay, something the higher thing what we have to do is try with the different templates and make the problem complicated.
I would agree that synthetic systems due to the polydispersity are more tricky to analyze as you have more than one template necessary to actually analyze the population of objects that might be somewhat similar or simpler in biological context. However, in biological context is of course a little bit worse from a scientific point of view. Now, you have been using quantification of images throughout the thesis. One example being the two-component polymer tape where you then quantify, for instance, position, thickness, and a number of different layers. What other measures could you apply to that system or similar system, and would you actually change what you measure depending on which application you have for the material?
Are you talking about the multi-layers?
Yeah, the multi-layer tape. That would be page 82, 84.
Yeah. I mean, the page 82, 84, yes, the multi-layers, what I have measured there is, first of all, is to analyze quickly whether the processing is good or bad. So that was my motivation in this specific analysis. So that one I tried to measure by the waviness of the layer, like trying to find the defect location and measuring laterally which location has the huge number of defects. But this can be further extended to measure the crystallinity, how much percentage of crystallinity are there, and also the
Is that something relevant for the application? Or?
Well, yes, it is relevant for the application because at the end, this specific material itself is for the gas permeability. So, if you are having, usually the gas transportation takes place in the amorphous phases of the tape. So, depending on the crystallinity and the material, what you are doing, you can tune that. So, with this technique, we can also measure the crystallinity and the crystallized orientation, whether they are flat-on oriented or edge-on oriented, also we can measure. And other than that, the quality control, which I have already done.
So there's a wealth more of information.
Yeah, it is well, but yes, it is. We can measure, but I would also need to mention here that when you are measuring the crystalline orientation, it is going to be computationally very, very expensive. So that needs to be considered before going for the analysis.
Now, for my last question, I would like to guide you to page 196, where you state that the goal at the end is controlled assembly of closed-random system to understand how this assembly translates into functional materials. So now, with what you have been doing in your thesis, what would be the next steps with the tools that you have developed?
If you ask me the question, what are the things you can extend from this thesis? The tools which I developed is quite unique, that it can be used for this multi-scale analysis. And how it can be extended? We can extend this to as a tool-wise, we can extend this to including focusing in the bright field imaging, which I didn't do, and that can be extended. And the overall analysis can also be extended to three-dimensional analysis, and this will give much information when you are going for the...
Dank u wel, mevrouw de Pedal. Thank you very much for your clear statement. And it's noted again, using hour has passed. So after promovendus, the members of this committee will now into for further deliberations. In particular, committee members will discuss and critically assess your defense of your thesis in this last hour. But before we will do so, our first